Hey everyone. Okay, so now that you've seen the lecture on the basics of multi-core processing, most folks find it pretty helpful to go back through the key concepts and not just review them, but see examples of how they can be used together in modern processors. So let's do it. So you probably remember from the lecture that the running example was this piece of C code and what this code did is it ran through an array of input numbers, the array X, and it computed the sign of all of those numbers. Now, we talked about how a modern C compiler like GCC or Clang will take this piece of code and compile it to a sequence of instructions that runs on a modern processor. So here I'm focusing you in on the basic body of the loop, and that's going to compile to a fairly straight line sequence of instructions, which I'm showing here on the right. Now in the lecture, we started with the world's simplest processor. We said we were going to run this compiled instruction stream on a processor that had one instruction fetch and decode unit, one execution unit, which I often referred to as a ALU, arithmetic logic unit, and had one hardware thread or one execution context. So that's this blue box at the bottom. There's one set of registers. And what this core did is every single clock, it would run the next instruction in the instruction stream. So I'm highlighting the instruction in red. We'd perform the instruction, and then the core would continue on doing the next instruction in the stream. So this is a single core processor. It's a single threaded core, and it can run one scalar instruction per clock because it only has one execution unit. There's only one yellow box. Now we talked about this idea of superscalar processing. And a superscalar processor adds the ability to process more instructions at once. So now I've changed my processor. It's still a single core. It's still a single threaded core, but now it supports two-way superscalar execution, which means it can fetch and decode 2 instructions per clock. And now notice that there's 2 ALUs to perform those instructions. And on the left, I'm showing you 2 orange bars to highlight the instructions that were chosen by the processor to run at the same time, because these instructions are independent. I can multiply R0 by R0 and add R0 with R0 at the same time. Now notice in the processor on the right, I've added an additional little box that's called instruction selection, and I put that there to kind of represent all the more complicated logic that a processor needs to have to determine whether or not instructions can be executed in parallel for correct execution. Okay, so that was superscalar execution. We were still running one thread, but we were running multiple instructions simultaneously from that thread. Okay, so now let's put aside superscalar for a second and go back to another form of parallelism that we discussed in the lecture, which was SIMD execution. So here's a core that is a single core. It's single-threaded. There's only one execution context. It does not support superscalar execution because there's only one fetch and decode unit. But we added multiple ALUs, 8 ALUs in this case. And so now this processor can perform the same instruction on 8 pieces of data at once. And if you look at the program on the left, I've changed all the instructions from being scalar instructions on scalar registers to vector instructions that work on vectors of size 8. Notice there's a vector mul and a vector add. So this is a different compiled program now. So you may find it useful to think about there being 8 ALUs that all do the same instruction. It's probably even simpler to think about it as there's one big ALU that can run one instruction per clock on 8 pieces of data. And so that's kind of why I drew the boxes all together there. Okay, so again, this is a single core processor. It's single threaded. It can only run one thread at a time. But that thread can issue and the processor can compute 8 wide vector instructions. Okay. Now we can combine the two ideas we just talked about. We can combine superscalar and SIMD, and now I have a new core that can fetch and decode 2 instructions per clock. But this particular core has one ALU that can perform a scalar operation, like a regular floating point multiply, and another ALU that does an 8 wide vector operation. So this processor can run 2 instructions per clock if the instruction stream that it's running happens to have the right mixture of instructions, one vector operation and one scalar. And if you look at the program on the left, that is in fact the case. So 2 instructions are highlighted, one's a vector op and one's a scalar. Now this is still a single threaded core. All of this is happening within the context of a single thread. So now we can put aside the SIMD and the superscalar, and we can make the core multi-threaded. So now I take the execution context and I duplicate it. So now I have a processor core, single core processor. It's now a 2-way multi-threaded core. It supports the state for 2 threads at once. Now this core is not superscalar or SIMD, so I went back to a single fetch and decode unit and a single ALU. Now notice that to use this processor in full, we need to give it 2 instruction streams. So now I have 2 different threads of control out here on the left, and notice that they are at different points in their execution. Instruction stream 0 is on the second instruction, instruction stream 1 is on the third instruction. These threads can be on completely different points in their instruction stream because the hardware is tracking different PCs for each of these threads. Now, of course, we can put it all together. We have this multi-threaded core. Let's go add back in superscalar and SIMD processing. So now I have a single core that supports 2 hardware threads. It can execute 2 instructions per clock, provided one of them is scalar and one of them is vector. And in this particular processor design, let's just assume that those 2 instructions also have to be from the same thread. So you can think about this core, the scheduler, every clock is saying, I'm going to pick either instruction stream 0 or instruction stream 1. I'm going to look for 2 independent instructions from that instruction stream. And if it's the right mixture that I can run at the same time, I'm going to run that. So this is a multi-threaded core. It supports superscalar execution. And one of those instructions that are run in a superscalar fashion can be a SIMD vector instruction. Now you might be thinking, well, wait a minute, if we have this scalar ALU and this vector ALU, why do we have to find the work from the same thread? Why don't we look for any mixture of instructions across all the threads that can be run at the same time? And that would be a different processor design with a more advanced scheduler. In fact, here I drew such a processor where now it has 4 hardware threads, but it can draw instructions in any clock from different threads. So I'm showing you an example where the processor decided to run a vector operation from instruction stream 0, from thread 0, and a scalar multiplication from instruction stream 3. So all of these instruction streams, remember, they're different threads. They can be at very different points of execution. But in this example, I'm not only interleaving the execution of the threads, because I can run instructions from 2 different threads simultaneously, I actually have 2 threads making progress simultaneously at the same time. Now, everything that we just talked about, of course, we can replicate across cores. So here I'm going to take the single core processor and duplicate the core, and now I have a dual core processor. Each of those cores is 4-way hardware multi-threaded. There's 4 execution contexts. Each of those cores is 2-way superscalar. And each core can execute a single scalar instruction and an 8-wide SIMD vector operation per clock. And if you look down at the bottom, notice that now I've given this processor 8 instruction streams because there's 8 hardware thread slots. And in this particular example, core 0 decided to pull an instruction from its thread 0 and 3, and core 1 decided to pull 2 instructions from instruction stream 6. Now this is all cartoons that I've been giving you, but it's not that big of a step to using the same symbols or the same sort of set of cartoon diagrams to describe processors that are out there in the wild. Like, for example, one of the processors we have in our lab at Stanford is of the Intel Kaby Lake version. And that every core of that processor actually has the ability to decode, I think, up to about 6 instructions per clock. And there are 4 scalar ALUs and 3 vector ALUs. And so if an instruction stream, or the 2 threads, this is a dual-threaded core, if the processor can find some mixture of instructions from these two threads to fill up these execution units, it will definitely do so. So this idea is what Intel calls hyperthreading in their sort of public-facing material. Okay, so again, this was heterogeneous superscalar that combines scalar operations and 8-wide vector operations. Now, everything I've said, I've kind of used the language of CPUs a little bit. All the same principles hold on a GPU. Things work just a little bit differently. I've introduced all these concepts in terms of the compiler generating SIMD vector instructions. And on most GPUs, things work a little bit differently. So on the GPU is given a bunch of regular scalar threads. And these threads only issue scalar instructions. But the GPU hardware will look at the, in this case, 8 threads that its core has to run and figure out if those threads are running the same instruction. In this example, 7 of the 8 threads are running the exact same instruction. And it will execute that instruction for all of these threads simultaneously on a set of ALUs that operate in a SIMD fashion. So this is what NVIDIA publicly calls SIMT execution, single instruction multiple thread. It has many of the same characteristics as traditional SIMD. The difference is that the hardware is given all of these scalar threads and figures out when those scalar threads can be executed simultaneously on their vector ALUs. So in this particular case, notice that instruction stream 6 is not at the same location as the other streams. So that vector lane would need to get masked off, or that ALU turned off, just so that no progress was made on instruction stream 6, because this core can only run one instruction per clock. Okay, I'm going to defer details of, we're going to go into more detail about these GPU cores in another short segment, but I'll save a discussion of like how the multi-threaded, superscalar, and SIMD all fit together in a modern V100 GPU to another lecture or another short segment that I'll post shortly.